So we want to get from point A to point B as quickly as possible. And to organize how we think about that, to organize the options, the routes, let's think about a network. So let me draw an example network here on the whiteboard. The origin is A, you want to get to B, okay? Let's have a very simple model of travel times in this network. Let's just say that I'm going to annotate each of these edges with a number representing the travel time along that road in minutes to get from the start of the road to the end of the road. So let's say this one takes 3 minutes, this one takes 4 minutes, this one takes 1 minute, this one takes 5 minutes, and this one takes 2 minutes. Okay? And these are one-way streets, so you can only drive on the street in the direction of the arrow in this example. Okay? So you want to get from A to B, you want to get there as quickly as possible. So how would you do that? Well, this is not a hard problem to solve just by inspection. If you look at it, there's only 3 ways to get from A to B that respects kind of the one-wayness of all the streets. You can go over the top, you can go the northern route, okay? So that would take 3 minutes plus 4 minutes, so that's 7 minutes to go the northern route. You could go the southern route, so that would be 5 minutes plus 2 minutes, so that would be, again, 7 minutes. So northern and southern routes are tied at 7 minutes. And then there's the zigzag path, which has more hops, right? So there's more kind of, the list of the driving directions is 1 step longer. But in terms of the travel time, actually you'll get there in 3 plus 1 plus 2 or 6 minutes. Okay. So the zigzag path is the quickest route from A to B, taking 6 minutes. So what we just did, the way we determined the quickest or shortest path from A to B in this example is something known as exhaustive search, which is if you have a whole bunch of options, like routes from A to B, and you want to find the best option, like the one with the smallest travel time, one way you can solve that problem is by just going option by option and remembering the best one. That's what we just did. There were only 3 paths from A to B. We checked them all. The zigzag one was the best, so we were confident in proclaiming that the shortest route from A to B. So exhaustive search you can think of as an algorithm. It's a pretty straightforward algorithm. Examine every option, remember the best one. And if there aren't that many options, right, like in this network there were 3 options, that's actually simple enough for just humans to do by hand or by inspection. Okay, and so you could do this manually for, I don't know, dozens of options, maybe hundreds of options. But of course, then, if you think about carrying out exhaustive search by computers, well, modern day computers, looking through billions of options is generally not a big deal. So you might think then, you're like, okay, well, exhaustive search, straightforward algorithm, computers can do billions of operations, like probably we're just done, right? I mean, probably just like whatever problem that comes up, in practice, like for example, driving from, to your relative's place in a different state, whatever. Just use a computer, look at all the options, remember the best one. End of story. But is that true? Can we be sure that actually in the problems that we sort of solve in day-to-day life, like again, just how to drive to our relative's house, are we sure that there's only billions of options? Are we sure that there aren't like maybe much more than that? So to see what I mean, let me show you another example of a network. And it's a simple network. It's not going to be hard to figure out the best way to go from point A to point B, but it is going to suggest the limitations of the specific approach of exhaustive search. Okay. So we again want to go from A to B. And let's assume that in choosing a route from A to B, you just make 4, is this 4? Yes, 4 choices where you either take the northern route or the southern route, and each time you wind up back at the same place, okay? So to get to the next stop, you can go north, you can go south, and there's just 4 consecutive decisions where you just choose whether to go the northern route or the southern route, okay? And for example, maybe these are the travel times. Now, you look at this network, and just like here, you're like, I don't need a computer to figure out the shortest path from A to B. Here, you're saying, I still don't need a computer to figure out the shortest path from A to B, right? You're like, obviously, I go north, and then south, and then north, and then south again, okay? For a total travel time of, what is it? I guess 16 minutes, okay? Obviously, this is the best thing. Any deviation from the red route would just substitute a worse road for one of the ones you're already taking, okay? Obvious. However, let me point out, when you reasoned through this problem, you took advantage of an algorithmic shortcut. You did not reason about it through exhaustive search, okay? In the network on the left, there were only 3 paths, 3 possible options, okay? How many options are there to go from A to B? Well, 2 options for the first hop, multiplied by 2 options for the second hop, times 2 again, times 2 again. Okay, so number of paths from A to B, 2 times 2 times 2 times 2. Also known as 2 raised to the 4th power, also known as 16. Okay? That is how many different options you have, okay? Because you have an independent binary choice 4 different times, all right? Now, you took a shortcut. You were like, I don't even need to think about any path that uses the 2, because I would just substitute the 1 and it would be better. Okay, so you just sort of pruned in your mind anything that used the 2. Similar, you pruned in your mind anything that uses the 4 or the 6 or the 8, leaving you with the 1, 3, 5, 7 red path. Okay, but in your mind, you did an algorithmic shortcut. You did not do exhaustive search through the 16 options. Okay, that's the first thing that I want you to notice, all right? Your response might be like, okay, but so what? Like, it's a computer, so it goes through the 16 options. That's trivial for any modern computer to do. What's the big deal? So it's a little bit wasteful, right? It's still going to complete in the blink of an eye, okay? All right, well, imagine we had a longer whiteboard. We had one of those long rolls of tape we were talking about with Turing machines in episode number 1. And I replicated these binary decisions a few more times. So in this network, the number of options was 2 to the 4 or 16, okay? So imagine you had 10 of these. And again, think about driving like to your relatives in a different state, okay? There actually are potentially a large number of decision points en route from, I don't know, New York City to Cape Cod or something like that. So imagine there were not just 4 of these, but there were 10 binary decisions you had to make in a row. So now you wouldn't just have 4 2s multiplied against each other. You wouldn't have 2 to the 4, you'd have 2 to the 16, okay? Which is 1,024. It's always you're talking to a computer scientist when they just have all the powers of 2 like automatically memorized. Definitely means it's a computer scientist. Among friends, 1,024, let's call this 1,000, okay? That would be a pain as a human to go through. Obviously we could do it. A computer could definitely do it. Sorry, this is a 10, 2 to the 10. Looks like a 16, not a 16. And that's also a 0. Okay. What if it was 20? And again, it would not be that hard. I could literally, if I decreased my font size, I could write down this network on this whiteboard. Okay, it is not like a big network. Okay, it's a relatively small network. 2 to the 20, well, that's like 1,000 squared or 1,000,000. Okay? If you had 30 decisions to make, we're talking about 1 billion. 40 decisions to make, we're talking about 1 trillion. And 1 trillion starts getting significant, even for computers to do. I'm not saying it's impossible, but you start feeling the pain a little bit at 1 trillion for sure. Imagine you're driving from the West Coast to the East Coast, right? Imagine you have, I don't know, let's say at least 265 different decisions to make. Going from, I don't know, Burlington to La Jolla, okay? 2 to the 265. 2 to the 265. So exponential growth is a wild, wild thing, right? So many of us kind of are first taught this lesson through the power of compounding, right? And this is sort of another version of it. Exponential growth is really, 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 really fast, really fast, really fast. So much so that it defies human intuition. 265, and again, you can imagine writing down a network like this with 265 choices, right? It would not be hard. Okay, we could write it down, we could have it on this table, no problem. The number of different routes in that network, the number of options you would have to check if you were carrying out exhaustive search is, I'm not kidding, basically the number of estimated atoms in the known universe. 2 to the 265 is the estimate for the number of atoms in the known universe. Okay? So while exhaustive search would still be an algorithm in the sense of Turing, it would still be a recipe that, if carried out to completion, would indeed identify the shortest path. It is one that would defy our understanding of physical limitations. It is one that would not complete in our or anybody else's lifetime.